Hello, everyone. Welcome to Mankind in Training. I'm your host, Joshua Parr, and today we have the Sympy Rundown Part 2. Today we're going to be going over the first example is validation of Navier-Stokes theorem, and then we're going to get into a little bit of quantum mechanics. We're going to be finding the energy eigenstates and relativistic energy states of the electron in a hydrogen atom. And then there's some examples with matrices and Pauli matrices. So without any further ado, I'm going to share my screen. And we have a Finley Analytics Mankind in Training tutorial. First, we are starting with the Navier-Stokes del operator. And then we'll have some quantum mechanics examples, like I was saying. So I think firstly, I need to, if I remember correctly, I need to run this, creating the parameters of the circle in the parametric region. I need to run that, and then I need to run this. I'm importing Sympy, the symbols, and I'm importing the vector. And from the vector, we're importing coordinate system, parametric region, implicit region, and the vector integrate. And I'm creating a coordinate system and calling it C. Now, we are using the curl function to find the curve and the surface, the parametric regions here, and creating a variable f being the c times y, c times I, or ci, the dot is actually saying where the index is at. And we're going to run this. And it gives me my symbols. Now, representing the vector differential operator, usually represented in mathematical expressions as the nabla or the del operator here. We're going to get a cross product of the del operator. And then we're going to, there's a Boolean component here, which will tell you true or false. If it is true, you're going to want to do the do it on the component. And if it returns false, it will contain the derivative instances. Run this, and we get the derivative of zc, xc, yc, z of c, and k hat of c. And now I'm going to do it to the gradient field. And I'm going to get yc zc times I hat of z plus xc zc j hat c plus xc yc k hat of c. Now, representing the dot product between the operator and the given vector equal to the divergence of the vector field. The parameters, again, the vector, and again, the Boolean. The vector whose divergence is to be calculated. If true, same deal. So we'll run that. And now I want the cross product of my del operator. I want this particular cross product. And I'm going to do it. And I get xcyc j hat c plus negative xczc k hat c. Now I want to we are adding z to the operator and xcyc j hat c. We got the same answer as before. So now I'm showing an example of the curl function again. Here are our parameters. And it tells me that the curl of cx, cy, cz, and ci all multiplied together would be this right here. x, y, c, j hat, c. So now, what happened here? All right. No, edit. Split cell. I'm not sure what happened there. Okay, now we're going to run that. And we get xcyc plus xczc plus yczc. And if I want the del op and this together, and we get xcyc plus xczc plus yczc. I'm not sure why my answers ended up coming into here. Here we are, xcyc plus xczc plus yczc. That's my divergence. Now, bringing in the del operator and the coordinate systems. This is all having to do with verifying Stokes' theorem, by the way. So, well, we did it again here. I thought I changed all of these. I copied and pasted it over from the notebook I was working on earlier, and apparently I did not separate these things. So, doing it here, yczc I hat c plus xczc j hat c plus xcyc k hat c. And now I just want the del op without the gradient. We get yczc I hat c plus xczc j hat c. So on, so forth. And maybe those do need to be there. Yes, they are, because they're specifying where I want. Yes, never mind. I've been deleting them. I suppose I should have been paying attention more before I started doing this presentation. I went through and gave it notes, but not on this top portion. I didn't do much of the top portion. Okay, so we have this again, where I need to split that up. And there we are. Run that. We get this curl plus I hat of z. Now, directional derivatives you can take by calling Sympy dot vector directional derivative. And I want the directional of this component here, this set of components. You get xcyc plus 4xczc plus 3yczc. And yes, again, we have specifying. So I get theta c zc. I wonder why that's not showing up. Because I would need to let's go theta equals SMP dot symbols theta. And now, Yeah, I wonder why that's doing that. It should be showing the symbol theta. I'm not entirely sure why it's not. So now if I want to ask if this field that I just created here is conservative, it will give me a Boolean, and it says that this is indeed conservative in a 3D coordinate system. So if I want to curl that field, you get the curl of the field is O hat. And so this is asking if the field is solenoidal, and it is indeed. This is asking for the divergence of the field, and it is 0. Now I'm importing Sympy.vector, and I'm asking for the scalar potential of this conservative field with respect to the R coordinate system. And it tells me 2xr, 2x of r, squared y of r, z of r. So we have scalar potential difference. We're asking for the scalar potential difference of this vector field using R and P. Tells me that that is 4. So now returning the energy of the state, we are over into the quantum mechanical examples. This is returning energy eigenstates of the electron in a hydrogen atom. The energy does not depend on L, and it's going to return them in Hartree harmonic units. The parameters are your n integer and your principal quantum number, which is an integer with possible values and any possible value. And then Z is, we have your atomic number, 1 for hydrogen, 2 for helium, is what you put in your Z category. So I'm asking for the NL state of N and Z, and it tells me it is negative Z squared over 2N squared. Now, if I want to find the N1 at 1, it is 1/2, negative 1/2. And if I want to find it at 2, it is negative 1/8. And if I want to find it at 3, it is negative 1/18. If I want to find it at 3, but I want to use the atomic number 47, bam. I believe 47 is silver? Silver? Yeah, instead of that. So, now I'm calling simp.physics hydrogen, and we get that here. But when I tried, I didn't like something here, returning the relativistic energy state. Anyway, so returning the relativistic energy state, NL, and the spin in Hartree atomic units, the energy is calculated from the Dirac equation. The rest, mass energy, is not included. N is your integer, L as an integer, also being your angular momentum in a quantum number with values ranging from 0 to n minus 1. And then spin up, true if the electron is spin up, default, otherwise down. And then Z again is your atomic number, and C would be the speed of light in atomic units, and the default is this value here as a constant. So now I'm importing the Dirac, and I'm finding the energy calculated from the Dirac equation at 1 and 0, at 2 and 0, 2 and 1, 2 and 1, with the false parameter at 3 and 0, 3 and 1, At 3 and 1 with false parameter. At 3 and 2. And at 3 and 2 with a false. So now we're into the wave function. We're returning the hydrogen wave function, NL of M, and the radial wave function, R of NL, and the spherical harmonic, YML. We have quantum number, angular momentum, magnetic quantum number, radial coordinate, phi, azimuthal angle, theta, and your polar angle, z, and the atomic number. So we're importing psi now, which is the wave function. And I'm creating all of these variables, and I am saying what they are, what they do. Now I want to return the wave function's values at 1, 0, 0, r, phi, theta, and z, and you get z 3 over 2 e to the negative zr over the square root of pi. Now if I want 2, 1, and 1, the same parameters, you get negative z 5 over 2, a real I, phi, no, it's r times e I phi, and then e negative zr over 2 sine theta, and then the root of pi, integrating the absolute square of a hydrogen wave function psi of NLM over the whole space leads 1. The normalization of the wave function is done as follows, and you do need to normalize it if you want to do anything with it. And it does indeed return 1, the normalization. I created a Jacobian, I created an absolute squared value of the conjugate of WF, and I defined WF as being the psi function with the parameters. This will return the hydrogen radial wave function. Again, we have angular momentum and a radial coordinate, relativistic energy states. And we have 2 times the square root of z cubed e to the negative zr. If I want 2 and O, you get the square root of 2 times negative zr plus 2 times the cubed, or times the square root of z cubed e to the negative zr over 2 over 4. I want 2, 1 position, square root of 6 zr square root of z cubed e to the negative zr over 2 over 12. If I want the 1, 0 position of just r, you get 2e to the negative r. For the hydrogen atom, you can just use the default value of z1, and you'll get these. For a silver atom, you need to change your z to the corresponding number of the particle you're trying to, or the element you're trying to find. And for the silver particle, we have 94 square root of 47 e to the 47 negative 47r. Run that. 2, 0. It expands out 47 to the square root of 94 times 2 minus 47r e to the negative 47r over 2 for 4. And as you can see, it keeps expanding out as we go further out. The normalization of the radial wave function is done as such. Integrate. And integrating from r to 0, or integrating r from 0 to infinity. 1, normalization. 1, normalization. one normalization. And this holds for any atomic number. Change the atomic number to, got helium, change number, atomic number. We have normalization of all of them. So now we want to return the energy of a one-dimensional harmonic oscillator. Parameters, your nodal quantum number, omega, the harmonic oscillator of the angular frequency, and the unit returned value matches the unit of HW, since the energy is calculated as En equals h bar times omega times n plus 1/2. So we're importing quantum harmonic oscillator, one-dimensional, and the En. And here we are. We have h bar omega times x plus 1/2. And now this will return the wave function of psi n for a 1D quantum harmonic oscillator, adding the x coordinate and the mass of the particle being m, and the angular frequency again being omega. Now we're importing psi from the quantum harmonic oscillator. And once we run psi of what we just ran up here, we get the root 4 of m omega e times negative m omega x squared over 2 h, and over the 4 root of h bar times the 4 root of, and returning the energy of an isotropic harmonic oscillator. We have a nodal quantum number, L. We have a HW, orbital angular momentum. And we have the harmonic oscillator parameter. And the unit returned will match HW, since the energy is calculated as ENL equals 2N plus L plus 3 over 2 HW. And we're importing. We got Z, 2x plus y plus 3/2. Returning the radial wave function, RNL, for a 3D isotropic harmonic oscillator. Adding new quantum number for the orbital angular momentum. This is the nodal quantum number, responds to the nodes in the wave function, and being greater than or equal to 0. And the mass scaled frequency, nu equals m omega divided by 2h bar, where m is the mass and omega is the frequency of the oscillator in atomic units. Here we are, 2 times 2 to the 3/4 e negative r squared over the 4 root of pi. And when I say that, like, if it just has the square root sign, it's square root. If it's got a 3 here, it's the cubed root. If it's got a 4 there, it's the 4 root. It's got so on and so forth. But that's the convention there. Now, if 4 was out here and it was normal sized, it would be 4 times the whatever happened to be their root of pi. I need to explain some of these things better, because I had all the notes up and the examples, and I should have just transferred those over as well. But I was just kind of copying and pasting from my other notebook into this notebook, and I made some oversights. L, nu, and R may be symbolic. Here we are. 2 times 2 to the 3/4 square root of nu 3 over 2 e to the negative nu r of the 4 root of pi. And we have RL, 2L plus 1 factorial underneath of 2L plus 3/2 times 2L plus 2. And all of that times e to the negative r squared over the 4 root of pi. So the normalization of the radial wave function will be done like so. Taking the integral. and normalize it. Dot in, normalize. Dot in, normalize. And you can do it for whatever. You can do 110, 110, 01, 001. Return the Dirac gamma matrix, gamma to the mu in standard Dirac representation. If you want gamma of mu, use gamma mu true. So we're importing M gamma, and there's a matrix, the M gamma matrix 1. Now this is going to return a Pauli matrix, sigma I, with I being equal to 1, 2, or 3. That should be in a parentheses. I'm not sure why it's not. I wrote it that way. Sometimes Markdown does not do what you want. So here's the sigma matrices. Here we are. So real quickly, I'm going to show, insert cell above. So quickly-ish, I'm going to go to Markdown. I just made this a Markdown cell, and I'm going to show you how to, like how I wrote this right here. You can write whatever you want here. But if you want it to be like mathematically represented, you would go sigma, like this is how I wrote this here, underscore if you want to do a sub, and then within some curly braces, I put the I part, and then over here we have I equals 1, 2, 3. And you run that. Yeah, that's weird. It did it that time. But yeah, you pretty much write whatever. Tabla new dash theta to the power of e times n plus 1 and another $sign at the end. You can write them. You can write just about whatever you want mathematically, and you use the math latex, and that's how you do that. You just go up and make your cell a markdown cell, and you have to use $signs before and after. So we have another matrix example. Matrice example, parallel axis theorem matrix. Inertia for the matrix, dy dx dc for a body of mass m. Translating the body of mass to 2 units of distance of 1 along the x-axis. We would get this here. Bing. Bing. Help function to evaluate the Pauli matrices product with the symbolic objects. Pauli 1 and I Pauli 2. And we get sigma 3, negative sigma 3. And x squared times Pauli 2 times Pauli 1. We get negative ix squared sigma 3. Quantum theory of many particle systems, and here's a bosonic annihilation operator, creating a b of x, calling second quantization, creating a b of x. So now I'm applying the state to itself if the self is not symbolic and the state is a Fock state ket. Else multiply itself by the state. importing bra and bracket at yb of x, yb sub x. And then if I want just the 0th element, I'm going to apply the bracket operator to the number. I get the square root of n, and then n minus 1. The fermionic annihilation operator, applying the state to the self. And if the self is not symbolic and the state is a Fock state ket, else multiply the self by the state. Now I'm importing the dagger operator, which is indicative of be doing some Kronecker sums. And doing the operator only to the 0th element, and we get what we got above. Always destroy a quasi-particle, annihilate whole or annihilate the particle. And this will, I'm making A, I, and P above Fermi and below Fermi. Importing second quant and F for Fermi. And I want to know, run that. So I want to know if F of A is only a Q annihilator. It's true. I want to know if I now is only a Q annihilator. It says no. I want to know now if P is an annihilator. And it says no. So the only thing that is going to destroy that quasi-particle is A. Always create quasi-particle is Q creator. Again, same parameters, runner. And is A Q creator? Nope. Is I a Q creator? Yes. Is P a Q creator? No. So now I want to store the upper and lower indices in each separate tuple. Each group of indices may be assumed to be anti-symmetric. And I'm importing the anti-symmetric tensor, creating I and J being below, and A and B being above. And we get V, AI, and BJ. Now, and you get the negative of the exact same thing. And as you can see, the indices are automatically sorted into a canonical form. Now, if you want to return the lower, here we are. You get B and J. Now, if I want to return the upper, it could return A and I, and it does. Returns the symbol of the tensor. B. Now we're going to do some commutators. Importing commutate B with A, negative AB. Commutate BA with respect to get AB. Yep. Now I want to do it. You get AB minus BA. That's the commutation. So for second quantization operators, the commutator is evaluated immediately. So I'm giving it a P and Q now. And I want to commutate FDA and FDI. And I get to AA dagger to AI dagger. But for more complicated expressions, the evaluation is triggered by the do it call. Okay. So now I want Wix equals true. And it gave me my Kronecker sum. We got negative delta sub IP, A sub Q dagger, plus delta IQ, A dagger P. And we have here quantization again, commuter doing the creating a value C that is the commutator operation of FGA, FI, FDB, and FJ. And again, I Wix because I want Kronecker sum 0 to gain and 0. So the bosonic creation operator, importing B dagger and B cat, and I'm using the dagger operation on B of X and applying operator Y. Get Y, B sub X, and if I just want the 0 element there, we get square root of n minus 1. So a fermionic creation operator, apply operator state, and if the self is not, if you apply the state to the self, and if the self is not symbolic, and state is a Fox state cat, else multiply the self by the state. And we get Y B sub X, if I want B naught. So now I'm asking if this is an annihilator again of these systems. Returns false that A is an annihilator. Returns true that I is an annihilator. And returns false that P is an annihilator. Again, we're doing the is only creator example. I want to know if A is a creator. True, it is. Is I? No. And is P? The answer is no. This was I went through this really fast, and I probably should have looked and made sure all my cells got separated where they needed to get separated, and I had the correct parameters in for all the things. I was trying to write up the notes for all this really quickly this morning because I have a bunch of other things that I need to do, but I wanted to do this to show the power of Sympy and all the different things that you can do. Verifying Stokes theorem with a computer is crazy, and being able to do all of this quantum mechanical operations is nuts. The sheer power of SymPy, SciPy, NumPy, if you can use all of them in conjunction with each other, you can solve just about any problem you need to solve. So thank you everybody for watching and Mankind in Training. And I'm your host, Joshua Parr. Thank you for showing up and watching. If you like, subscribe.